Let's begin with something uncomfortable. Modern CPUs lie to you. Not in a malicious way, not in a broken way, but in a carefully engineered, deeply sophisticated way. You write instructions in a specific order, line after line, step after step, and yet inside the processor, those instructions are very often executed in a completely different order. Not randomly, not incorrectly, but out of order. And if that sounds dangerous, it should. Because preserving correctness while reordering execution is one of the most complex engineering achievements in computing history. Today we are going deep into out-of-order execution, not the simplified explanation, the real mechanism. We're going to cover why in-order pipelines hit a wall, what dynamic scheduling actually means, how register renaming removes false dependencies, what the issue queue really does, how the reorder buffer preserves correctness, why memory makes everything harder, what speculation adds to the equation, and where the real performance limits are. This is one of the most important topics in software execution. Let's start at the beginning. Imagine a simple pipelined processor. Instructions move through stages: fetch, decode, execute, memory, write back. In an ideal world, one instruction completes every cycle. Now imagine this instruction sequence. Instruction 1 loads data from memory. Instruction 2 adds 2 registers. Instruction 3 multiplies 2 registers. Suppose the load misses the cache. That one load might take hundreds of cycles. In an in-order processor, everything behind it waits, even if Instruction 2 and Instruction 3 have nothing to do with that load. They stall, execution units sit idle, throughput collapses. This is the fundamental limitation of in-order execution. The processor obeys program order strictly. If something blocks at the front, the whole pipeline backs up. Now here's the key insight that changed CPU history. Program order does not always equal dependency order. Those are not the same thing. Just because instruction A appears before instruction B in code does not mean B depends on A. If B does not need A's result, there is no reason it must wait. That observation is the birth of out-of-order execution. Out-of-order execution allows instructions to execute as soon as their inputs are ready and the required execution units are available, regardless of their original program position. But this introduces a huge problem. How do you reorder execution without breaking correctness? That's where the machinery begins. Let's break down the structure of a modern out-of-order call. The pipeline is usually divided into 2 major halves: the front end, the back end. The front end fetches instructions, predicts branches, decodes instructions, and performs register renaming. The back end schedules, executes, and commits instructions. The magic begins right after decode. When instructions are decoded, they still reference architectural registers, the registers defined by the ISA, like RAX or R1. But architectural registers are limited. If you reuse the same register name multiple times, you create artificial dependencies. There are 3 kinds of dependencies: read after write, true dependency; write after read, anti-dependency; write after write, output dependency. Only the first one is real. The other 2 exist because registers are reused. Out-of-order execution relies heavily on register renaming. Instead of directly using architectural registers, the processor maps them to physical registers from a much larger pool. If you write to R1 3 times in a row, the processor may assign 3 different physical registers. This eliminates false dependencies. Now, instructions that were artificially linked are free to execute independently. After renaming, instructions are placed into structures that hold them until they are ready. This includes the reservation stations, or issue queues. Think of the issue queue as a waiting room. Each instruction waits there until its input operands are available. An appropriate execution unit is free. Each cycle, the scheduler scans the queue. It selects instructions whose dependencies are satisfied. Those instructions are issued to execution units. This is dynamic scheduling. It happens in hardware. It happens every cycle. It tracks dependencies across potentially hundreds of in-flight instructions. This is not simple logic. The scheduler must know which physical registers contain valid data, which instructions are waiting on which results, which execution units are busy. As instructions complete, they broadcast their results. This is sometimes called result forwarding or wake-up logic. Other instructions listening for that result now become ready. They move from waiting to eligible for issue. The processor constantly hunts for ready work. If instruction 10 is ready before instruction 5, it may execute first. That is out-of-order execution. But now we face the most important question. If instructions execute out of order, how does the processor ensure the final result matches program order? This is where the reorder buffer comes in. The reorder buffer, often called the ROB, is the structure that maintains the illusion of in-order execution. When instructions are decoded and renamed, they are allocated an entry in the reorder buffer. Even if they execute early, they cannot commit their results to the architectural state until they reach the head of the reorder buffer. Commit happens strictly in program order. If an earlier instruction has not completed, later instructions must wait before committing. This ensures precise exceptions. If a fault occurs, the processor can roll back to a known good state. The reorder buffer tracks destination registers, completion status, exception flags, branch prediction information. When the instruction at the head of the ROB is complete and no exceptions occurred, it commits. Its result becomes architecturally visible. Then the ROB advances. This separation between execution and commitment is critical. Execution may be chaotic. Commitment is disciplined. Now let's add memory to the picture. Loads and stores complicate everything. Two loads may execute out of order safely. Two stores must commit in order to maintain memory consistency. A load must not read from a store that has not yet committed if that store is earlier in program order. Processors handle this using structures like the load store queue. The load store queue tracks memory operations and enforces ordering rules. Speculative loads may execute before older stores complete. If the speculation was wrong, the processor must roll back. Which brings us to speculation. Out-of-order execution is almost always combined with branch prediction. If the processor waited for every branch to resolve before continuing, it would stall constantly. So it predicts branch outcomes and continues fetching and executing instructions along the predicted path. Those instructions are speculative. If the prediction is correct, great. If the prediction is wrong, the processor flushes the speculative instructions and restores the architectural state using the reorder buffer. Speculation increases performance massively, but it also increases complexity and power consumption. Now let's talk about performance limits. Out-of-order execution depends on several factors: issue width, reorder buffer size, issue queue size, physical register count, branch prediction accuracy. Cache performance. A small reorder buffer limits how far ahead the processor can look. A small issue queue limits scheduling flexibility. Limited physical registers restrict renaming freedom. Poor branch prediction reduces effective instruction window. Frequent cache misses stall execution. Modern high-performance cores may have reorder buffers capable of holding over 200 instructions. That means the processor may have hundreds of instructions in flight simultaneously, all being tracked, all being scheduled dynamically. Now consider the power cost. Every cycle, the scheduler checks readiness across dozens or hundreds of instructions. Dependency tracking grows complex. Wakeup and select logic consumes energy. Result forwarding networks grow expensive as execution units increase. This is one reason efficiency cores often use simpler out-of-order designs or even revert to in-order designs. There is a trade-off between performance and power. Now let's ground this in software engineering reality. What does out-of-order execution mean for you? It means latency can be hidden. If one instruction takes many cycles, the processor may execute other independent instructions in the meantime, but only if those independent instructions exist. Long dependency chains limit instruction-level parallelism. Tight pointer-chasing loops reduce scheduling flexibility. Unpredictable branches shrink the effective instruction window. Cache misses reduce usable ILP. Good performance-oriented code increases independence between operations. Loop unrolling increases visible parallelism. Reducing unnecessary dependencies helps the scheduler. Data locality reduces memory stalls. Out-of-order execution is constantly trying to rearrange your instructions to maximize throughput. If your code provides opportunities, it will exploit them. If it doesn't, the hardware cannot invent them. Now, let's talk about precise exceptions. One of the hardest problems in out-of-order execution is handling faults correctly. If instruction 20 causes a page fault, but instruction 25 already executed, how do you prevent architectural corruption? The reorder buffer solves this. Because instruction 25 has not yet committed, its effects are still speculative. When instruction 20 faults, the processor stops committing further instructions. It discards younger speculative instructions. Architectural state rolls back cleanly. This is what makes debugging and operating systems possible. Without precise exceptions, chaos would follow. Now consider scaling. Why not build a 16-wide, 512-entry reorder buffer monster core? Because complexity grows rapidly. Scheduling logic grows quadratically with issue width. Bypass networks become wiring nightmares. Power consumption explodes. Diminishing returns appear because most real-world code does not provide unlimited instruction-level parallelism. So modern CPUs balance: moderate width, deep reorder buffers, aggressive branch prediction, strong caching, and multi-core scaling. Out-of-order execution was one of the last great single-core performance multipliers before frequency scaling hit thermal limits. It extracts performance from existing code without programmer awareness. It is invisible. But it is constantly working. Now let's tie everything together. The flow looks like this: fetch instructions speculatively, decode them, rename registers, allocate reorder buffer entries, place instructions into issue queues, wait for operands, dynamically schedule ready instructions, execute them on functional units, write results to physical registers, mark instructions complete in the ROB, commit in order. That entire dance happens every clock cycle, billions of times per second. Out-of-order execution is not a minor enhancement. It is the core reason modern CPUs achieve high IPC on real workloads. Without it, superscalar width would be severely underutilized. Without it, memory latency would dominate execution time. Without it, branch mispredictions would be catastrophic. It is one of the most sophisticated illusions ever engineered. Your program appears sequential. The hardware is anything but, and yet correctness is preserved. That's the brilliance. In the next evolution of this series, we can go even deeper into specific components. The reorder buffer in isolation, branch prediction in isolation, or memory ordering models. Because once you understand out-of-order execution, modern CPUs stop being mysterious. They become systems that aggressively pursue parallelism within the boundaries of correctness and physics. And once you see that, performance engineering stops being guesswork. It becomes architectural alignment. I'll see you in the next deep dive.